So chapter 6 is on one-way layout. Do we or have we ever heard of the phrase one-way layout before? No. Have we ever heard of ANOVA before? One person. Analysis of variance is a technique that is used in a one-way layout. What is this one-way layout that we talk about? We have, say, K treatments of some sort. And let's say TK is the effect of the K treatment. By treatment, I don't necessarily mean a drug. It could be anything. It could be great. It could be money of some sort. Doesn't matter. Some attribute. So let's tau. Tau's of K. Tau Greek. And epsilon normally distributed noise. Okay. I believe your book uses theta, and the parameter that they refer to is the median. And mu is simply the overall mean. K treatments. If I collect an observation of some sort from any of these treatments, let's just call it as YK. YK would be the observation from the K treatment. I need two indices because when I do Y sub IK, that means the ith observation from the K treatment. Good. So in the first sample, this would simply be Y11, Y12, excuse me, Y21, Y31, dot, dot, dot. I'll call it Y n sub J1, dot, dot, dot. because I can stop at n sub j. Likewise, over here, it would be y12, y22, y32, dot, 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 y two. At j, I can put it as 1, 2, corresponding to the treatment. So N2 observations from treatment 2, N1 observations from treatment 1. A similar manner, 1K, 2K. Hey, what's 2K? It was a thing. It was a thing. Y, N, K, K. NK observations from the K treatment. Good. Do we have to have the same number of observations? No, not. Let's say we take the overall effect. In other words, we just take the average. The ith observation is given by the overall mean plus the effect due to the kth treatment and noise that would result in variability. If I took the average of all observations in the first treatment, or generally speaking, the kth treatment, we can denote it by that. It's a standard notation. When we write it as y dot k, we're summing over all i's and then dividing by the sample size. You get the average. If that bar is not there, it'll simply be the sum of the observations in the case treatment. Good. So here, this is the average in the case treatment. Good. It's great and all. When I take, let's say I've got a bunch of observations. This is some fixed value, that is a constant. If I take the average of mu's, what would I get? Overall mean, underlying mean is a constant. And let's say I have NK observations. Let's even put it or look at it from a practical sense. We'll say mu to be 2. NK, fifth treatment, N sub 5 is 20. So you have 20 observations in the fifth treatment. The underlying mean mu is 2. What is the average of all the mu's? 2. In other words, it'll simply be mu. Do you agree? I'm looking at the kth treatment. Yes? Let's say the kth treatment has an effect of 4. I'm taking the average of 4, 10 fold. What would I get? Huh? What is the average of 10 folds? still 4. So when I take the average across the MK observations, I will still get 1000 K. Now, this is the statistical theory. Theoretically, what is the average of epsilon r? All things considered, 0. Because our assumption is that it is normally distributed with mean 0, variance 1. Correct. That part would go away. This is all we would have. In practice, that number is going to be relatively small. So we can ignore that, and this is what we will have. What is the goal? Our objective in a one-way layout. Why the name one-way layout? Layout, one-way.
400 different things. Like 400 different things in one way.
What makes that up? So in a one-way layout, the K treatment mean is given by this. Overall mean is mu. Underlying effect for the K treatment is 1000 K. Could the overall mean be 0? Yes, it can. Here is the question. So, what would it mean if there are no differences in the treatment means? Tau K would be 0 for all K. Yes, that is one of the tests that we can do. But what is another way of looking at it? If there are no differences at all, that is perfectly fine. That's one way of looking at it. What is another one? The treatments have no effect. How could we write it as a mathematical expression in terms of taus? How are tau 1, tau 2, tau 3, tau 4, tau all the way up to tau K related? They're all equal to each other. Good. So, yes.
Sorry, what does it say or quotations, or is it an average of the
N sub K. N sub K. So that's pretty much what we're saying. So the norm is just that. The alternative is not all treatments. Do you agree? We can't, I mean, sure, we can write it using mathematical notation over here. That would be painful. Right? Let's just leave it this way. Common mistake people would say the alternative would simply mean they're all not equal to each other. They're all different. But that's not the case. They don't all have to be different. If one of them is different from the rest, then that's false. Correct? You don't have evidence to it that. So you can't say all treatment effects are different. You could say not all treatments are the same in the sense at least one of the treatment effects are different. Good. So don't make that mistake. When people look at this null, immediately they will write the alternative as tau 1 not equal to tau 2 not equal to tau 3, all the way not equal to tau k. But that is just one possibility. Yes.
So one-way layout is the same as ANOVA,
Yes. That's exactly what
and
I'm going.
ANOVA is non-parametric.
I'm not there yet. Patience, my young Padawan. So, one-way layout, yes. That is the hypothesis for a one-way layout. The assumption is there is an underlying need. There is a treatment effect. Epsilon I normally distributed. If I want to test the hypothesis, this one-way layout, then I can use analysis of variance. That is a statistical test. But analysis of variance has a bunch of assumptions. One of the key assumptions of analysis of variance is that epsilon I is normally distributed. It has to be a bell curve. If the noise is not bell curve, then we can't use ANOVA. Two, data typically have to be continuous unless you have really large samples, in which case it wouldn't matter. Another assumption is that the populations have to be independent of each other. Populations, treatments, they mean one and the same. So they should have no connection whatsoever. If they are independent, if epsilon I are normally distributed, then I can use ANOVA. So independent, identically distributed, that is a strong assumption that ANOVA requires. So to verify that one-way layout hypothesis test, H2 hypothesis test. The parametric version yes. And the assumption here IID stands for independent and identically distributed normality bell curve. Now, what if the assumptions are violated? A nice way to violate the assumption is to collect really, really small samples. For instance, if I simply had 4 observations in treatment 1, 2 from treatment 2, 4 from treatment K or 3, then one simply cannot use ANOVA. You may say, well, then collect more data. Well, it's not that easy. There are cases where the best we could do is a small sample. That's why we have a non-parametric test. One, you don't have to be particular about assumptions. Two, small sample. Good example, let's say if you want to test the drug, test the effect or side effect of a drug on people, perhaps you could get, 10 volunteers each. But for us to say, well, I'll go ahead and collect 100 people and subject this treatment to 100 different groups. So let's say K different treatments, 100 each, lots of people. And I want to know if they all experience some sort of a side effect. Too risky, right? In some cases, we can only do a small sample. Happens all the time. Biology, sciences, all the time. How does ANOVA work? Why do we call it analysis of variance? Do all of those variances, do you think that all of the observations that you collect from treatment, hypothetically, would they be the same? Absolutely not. The purpose of that epsilon I is to introduce variance. Yes? Do make a change. Earlier, I wrote epsilon I to be normally distributed 0, 1. Yes, that is the standard case. Typically, we observe 0, 1 noise. But sometimes you could have any variance. So generally speaking, it's 0 sigma squared. So I'll put it here. It doesn't have to be 1, but for the most part, it's 1. That is the part that's going to introduce variability. If I find variability within a sample to be very small, then I could say the observations that I collect from here are consistent. Would you agree? Yes. I make repeated measurements, I end up getting 10.1, 10.2, 10.3, and so forth. Visually seeing it is better. I'll just use 3 treatments. K is 3. Yes. This is what happened. If you can't see the observations, do that. So the first treatment, I wrote 10.21, 10.19, 11.41, 10.99, 10.8. Second treatment, 9.81, 2.89, 10.81, 10.11, 10.21, 10. 10.99. Last case, 10.99, 10.21, 10.41, 11.89, 11.01, 9.01, and 10.1. Good. Of the three treatments, which sample do you think would have less variability? Would it be treatment 1 sample, or sample from treatment 2, or sample from treatment 3? Less variability. The least variability. 1. Pretty consistent. Most variability.
Number 2.
2. That's probably going to come next. Okay. If you have a sample of this size, what does an ANOVA do? ANOVA finds variability within and the variability between. Good. So it measures how things vary within each treatment, puts them all together, takes the average of within treatment variance. Then it looks at the variance or variability between treatments. Variance between 1 and 2, 1 and 3, 2 and 3. Takes the average of sorts. I don't want to get into ANOVA, that's a huge derivation in and of itself. So if the ratio of the differences, let's say between if the variability between the treatments collectively, think of it as the average variability between treatments. If collectively the between variation is bigger than the within variation, would you consider the treatments to be significantly different or to be the same? You want me to repeat the question? If the variability between treatments, average collective value, in other words, variation between 1, 2, 2, 3, 1, 3, everything put together, if that between variance is bigger than the within variation, again, collectively, within, put together. So if that between variation is bigger than within variation, would you conclude that the treatment effects are different or they're the same? Different. So if this is 10, that is 2, and that is 5, the between variation is going to be 9. Do you agree? But if this is 10, that's 10.1, and that is 10.4. Between variation is going to be small. So that ratio is simply a ratio of variances. Good. Hence the name analysis of variance. Do we get it? We usually F it up. That will have an F distribution. We're not going to do that. So that's how ANOVA is done. Good. So that is the parameter. If the assumptions are satisfied, then we compute this ratio. And if we have to reject the null, in other words, there is one treatment effect that is significantly different than the rest, the numerator value would get significantly larger so that you reject the null. Good. Analysis of variance. If the assumptions are violated, then to test whatever we talked about, in a non-parametric sense, It is called Kruskal-Wallis test. Erase.
And this test requires less data? Or does that not matter? When you say parametric version and the non-parametric version, isn't that just have to do with sample size?
Yes, the parametric version requires typically reasonable sample size for it to be a good test. Two, it has to satisfy assumptions. If epsilon I is not normally distributed, then this ratio will not be an F distribution. We can't F it up. If it's not an F distribution, you can't use an F distribution to reject or not reject or to find a p-value. Do you agree? It has to follow. The only way that this ratio will follow an F distribution theoretically is when these assumptions are satisfied. The non-parametric case though, it doesn't matter. Small sample size doesn't matter. All I care about is the treatment or the effect size. That's it. How do we go about doing it? Well, suppose I put the observations, all of them, in order, just like Wilcox and Blankson. Combine them all together, order them. We combine all K treatments, put all the observations together, just like Wilcox and Ransom. And if I start assigning R, I, J, the ranks after I combine. The ith rank, the rank of the ith observation in the jth treatment. J could be from 1 through K. So I 1, 2, dot, 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 up to NJ, J 1, 2, dot, 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 up to K. If I pick 3 treatments, what are the possible cases? 1, 2, all the way up to N1, 1, 2, all the way up to N2, 1, 2, all the way up to N3. It's 1, 2, all the way up to N3 because J equals 1, 2, all the way up to K, which is 3. Guess I can erase this. say RJ is simply the average of the combined runs in the J sample for the J treatment. Good. I think your book uses H. H is the Kruskal-Wallis test statistic. I'll just keep J to be consistent. So you rank, you put the observations together, rank them in a combined fashion, very similar to Wilcoxon rank sum. Then you take the average of the combined ranks in the Jth treatment. That would be RJ. And so J is the sample size for each of those treatments, N1, N2, N3. Evaluate that minus 3 times uppercase N plus 1. Good. If you have to take a guess, what is uppercase N?
Total of all sample sizes.
Total of all sample sizes. Good. We sum all the sample sizes. That's what we would get. So that is what we call the Kruskal-Wallis test statistic. What distribution does H have? Kruskal-Wallis distribution. Just like Wilcoxon sign rank distribution, Wilcoxon rank sum distribution, Kruskal-Wallis distribution. It has a distribution. I'll show you using R how to do that. But does this make sense? Intuitively, to a certain degree, it should, but there is a huge derivation for this. I'm not going to do that. If they're all pretty close to each other, and then you put them in order and you rank them, do we expect a really large value for H? Forget about the sample size because I keep dividing by the sample size. So increase the sample size, things would get normalized. But the RJ, the averages that you pick for each case, would it be small or large if the ranks are pretty close to each other? That value will be small. This will, by all means, whatever number you get here will be bigger than that, no matter what. It'll be positive. It's a positive test statistic. So this would become small, and you get closer and closer to a small value you won't reject. But if the ranks get bigger and you have more of bigger ranks, and when you average, the big ranks take over, this number will blow up. If that blows up, the entire term would get bigger, significantly bigger than that, larger H, reject the null. Does that make sense? Same concept there, it's based on variation. Here, it's based on ranks. Every single time we did a large sample approximation, what distribution did we use? What did we do to the test district? We standardized. When we standardized, what did it end up becoming? A normal distribution, right? Do we remember that W becomes Z, U becomes Z, normal distribution? That is with those. Here, large sample, H. H will approach a chi-square distribution. With df equals k minus 1. Good. The nice thing about this large sample approximation is that you don't have to standardize at all. No standardization necessary. If the sample size is large enough, H can be approximated with a chi-square distribution. So to do a large sample approximation, we just use chi-square distribution with df equals k minus 1. Typically, if a square appears in a non-parametric test statistic, then its large sample approximation will be a chi-square. Good. Square there, chi-square. Most cases, since I'm a statistician, I would say 99.99%. Not 100% because I don't know every single case. But anytime a test statistic has a square, its large sample approximation will end up being a chi-square. Good. Which is why I call normal distribution to be the mother of all distributions, chi-square to be the father of all. Good.